find a way to find your way to last year's one. That's you? Okay. So what? Okay, I don't have anything to do now. You're not seeing mine, right? Okay. Sorry, where was I? Yeah, so problem of the week 0. So here's what I'm going to do. So I had a bug that I had to work out of the problem that I was trying to give you, and I couldn't give it to you with the bug in it. I got the bug out. But for those of you who spent some time working on that second problem from last year, to save you that, I'll bring it forward. So it'll be part of the set for the one that's for this year. When it pops, you will see that question in addition to 2 others. And the 2 others are related. They're very similar. In fact, the code for one can help you finish the code for the other. So, you know, I hope you will get your maximum marks from it. And by the way, every week's own assignment is out of 50. So if you see the total adding up to 75, that actually means that you can get more than the 3% in that week. Okay? So it's bonus. You understand what I'm saying? Your reaction doesn't seem to imply that that was good news. But that was actually good news. All right. Okay, so that's the problem of the week. And once I'm done with this lecture, I have another lecture afterwards. But this afternoon, by this afternoon, it should become available. And you should see 3 problems on it. Okay. No question. This one is going to expire on the Sunday because it was just for practice. The real deal will start Sunday morning. Well, Monday morning, midnight. Sunday night, midnight. Night, which one you prefer? It's the same time.
Sir.
Somebody's saying hello to me.
Yeah.
Speak.
Will the prior lecture be posted online?
Yes. Yes, they just haven't reached there yet.
Pardon?
Yes. The question is, will the old lectures be posted? The answer is yes. They just haven't gotten there yet. But they will probably get there. Once problem of the week 0 is released, you'll see the videos will also become available. Okay, so we're talking about orders of growth. And how I introduced it to you is we needed a way to compare functions. And you'll see why in due course. But the main thing is that, when we talk about an analysis of a program or an algorithm, we won't have an answer to that question. Like, how good is this program? The answer is not a number. The answer is a function. It depends on so when I ask you how many steps does a program take or how much time does it take to run, your question to me should be, what did you run it on? If you run it on very tiny inputs, it takes a short amount of time. If you run it on very large inputs, it might take a longer time. So what we're more interested in is, how does the running time vary with the input size? So that's a function. Now, if we're talking about functions, and so we're comparing 2 algorithms, 2 of them have different behaviors as far as that performance is concerned. We want a language. We want a way to describe this algorithm better than that one.
Sir, we cannot hear. Sir.
He's saying he can't hear any of the audio, not hearing the speech.
Meeting Sudan. Yeah. Kevin, are you hearing me?
All right, yeah, we're hearing you now.
Their end is muted. Yeah, I'm seeing that. All right, so in our analogy, we had big O, and I said to you that's like less than or equal to. And big omega is like greater than or equal to. Theta is kind of like equal, little o is like less than, and little omega was like strictly greater than. I'm going to actually give you formal definitions for these on the left. I know you've seen them before in discrete math. I'm going to give them to you again, and I'm going to give you an alternative definition that I think operationally is more useful. I don't know which definition you got in discrete math, but I do know that the traditional definitions of these involve describing existence of something, existence of a constant that can satisfy a condition. So let's get to that. And then you can see how,
Excuse me,
what I gave you as
what are the last two?
what we're trying to achieve here, you're going to see how these speak to that. They create a framework that allows us to make that comparison. So, first of all, our functions have to be on.
Excuse me, sir. What's the last symbol?
Typically natural numbers.
Just in the camp.
And typically we only care about the positive side of the function. So this is typically a function that is meaningful in the context of counting something or measuring something that's physical, whether it be space, time, what have you. So you don't have negative values. We'll say that.
Go ahead.
Sir, what is the last symbol?
F is big O of G.
Excuse me, please.
So this time, I'm actually, let me just put the variables in. You don't always see that, but it doesn't matter. We'll say that F of n is big O of G of n if you can find a point, so there's some point, some value of n, and there is a constant such that for all values of n beyond that point, so this, you can say this is eventually the f's are less than or equal to the scaled version of g. So that c is a scaling factor. And in my analogy, my description here before up until now, I was ignoring that c just to kind of keep the comparison and discussion conversational. But the formal definition allows you to scale up the thing you're comparing to. The reason why I want to, well, the rationale for that can wait. You'll appreciate that. But just a quick one-liner on that. We're going to use this to describe things like, algorithms, and we're measuring them. And we're going to want to divorce ourselves from a specific pattern or a specific model of a machine. And therefore, whether you have a machine that can do an operation that another one does in 2 steps or 10 steps will affect the scale factor, we kind of don't care. What we do care about is how many conceptual steps are necessary. And so if one function outperforms another one just by a scale factor, that doesn't count. That's not good enough to be considered as less than or greater than in this regard. So that's what that C does. If you can find a way to scale the G in such a way that eventually all the F's are less than or equal to that scale version of the G, then F is equal to G. So in that regard, G is kind of an upper bound on F, up to scale factor. That's how they say. Now, well, okay, I'm actually going to write down big omega as well.
Muted?
Those of you who are blocked by
You want
this.
it muted or you want it open?
Sorry?
So I have to find a way to do it on.
Hopefully you can look on the side. Is there a question? Somebody said something about constant?
Yes, sir, but you know what? I don't think you can hear.
C and N naught are constant. All right. So that was definition 1. Definition 2, we'll say f of n is big omega of g of n if there's a point n naught and a constant c such that eventually is at least as big as a scale version of g. One word on this notation, and this is perhaps a historic issue. It's really the mathematician's fault. This notation says f of n is equal to big O of g of n. It's kind of a misnomer, a kind of a misrepresentation actually, if you think about it very carefully. Because technically speaking, big O of g of n actually represents a whole set of functions. It's all the functions that satisfy this property. And so when we say f of n equal big O of g of n, technically speaking, what we really mean is f of n is a member of the set of functions upper bounded by a scale version. Okay, that's the right way to think about what that really means. Thankfully, for the most part, you're not going to need to worry about that too much. Right, now, so this is all well and good. And in fact, it can be a little bit painful to use these definitions, but these are kind of the original definitions. Let me give you a sense of how you might use this. So suppose I said to you, proof.
Can you turn off the lights? You can see?
Let's see, n squared plus 1 is big O, is 3n squared plus 1 of n squared.
Yeah. Yes. So turn the pump off again.
How do you go about doing that? You see that? Okay, according to this definition, what is it asking you to do? It's asking, can you find 2 numbers? Can you find n naught and can you find a c? So that when you scale the function inside here by c, it always is at least as large as this function at each of those values n. Do you feel yourself, if you're trying to prove this, now what you're doing is a search. It's like you're saying, what c should I use? What n naught should I use? You're kind of probing, and maybe you're trying a few things. Any guidelines? How would I pick a c to make this easy to prove? What might you choose? What? You want to show that eventually all the f of n is not bigger than c times g of n, and f of n here is 3n squared plus 1. Can you think of a c that you would scale this n squared by to guarantee that it's bigger? One? 4, yeah, okay. 4 is a lovely number to choose because 4n squared is going to be bigger than 3n.
All your time. If you leave it there, just drop.
It drops. Somebody type it in the chat, please.
And c equals
Bad. It's bad.
4. We want to show I'll write it out. We can show that for all n that are at least 1, 3n squared plus 1 is not bigger than 4n squared. Let's actually show that. This is a good way to do this. You've seen this before? So you're trying to prove that this is always less than that beyond some n. But that's not going to prove it. That's reasoning about it. But if you're trying to write it down in a way that's irrefutable, you don't want to talk about and so on. You don't want to be using those kind of phrases. What can I do? Well, I could do, yeah, okay, yes, you could pull out an induction, but then that's another whole story. That's another page of text. In general, when you have comparisons, you want to prove one side is less or equal to another. Do what? Subtract? Somebody said subtract? Did I hear that? All right. It's generally easier to compare to 0 than to compare to something else that's changing. So a good technique is to put 0 on one side and then look on the other side and argue. Can you argue that it is always either positive or negative? That's what you're trying to do. So in other words, I could just subtract this side from that and get, so I'm going to write this. So 3n squared plus 1, if that's supposed to be less than or equal to 4n squared, then that implies that, I hope you don't freak out. I'm just going to move, subtracting this from both sides and switching it around in one step. Because you're not in fifth form anymore, right? Sorry, third form. Whenever you first did this. And then that's going to give you n squared minus 1 greater or equal to 0. Now, when is this true? Well, I mean, I could just declare that that's obviously true once n is greater than 1. If you wanted to be completely rigorous and kind of go through it and say, oh, well, I could factorize this thing, and then if n is less than minus 1 or n bigger than 1, that's going to be true. And that's all fine. But remember that the f and g were understood to be on the non-negative values. So negative n are never valid anyway. So we don't need to concern ourselves with negative values of n. Not permitted, right? So this is going to be true if n is greater or equal to 1. And so we just proved it. That's what we're trying to prove. Now, why did I show you this? Because I want you to appreciate that. Question? Okay. I want you to appreciate that this definition, while true and accurate and correct and perfect in the sense of what big O is supposed to mean, if you're actually trying to use it in a pragmatic way, it's kind of cumbersome. if you wanted to prove this, you notice that we kind of had to do a kind of search for this constant. And these happen to be very simple functions. If the functions get more complicated, we want some more handy tools to help us quickly get to the conclusion. Because for us, we're not getting caught up in the validity of these things. We want to make correct statements quickly. Let the mathematicians worry about the soundness of it. What we're doing is we're standing on the shoulders of giants, if you wish. They've already done the hard work or proved that this is all good, and the things that you expect to work will work, and we just want to take advantage of that. So what I want to do is show you a different definition that would then enable us to do these kinds of, if you needed to prove something, you can prove it a little quicker, it's a little more straightforward. And then I wanted to get into some useful facts about when you combine functions and how we can then conclude the orders of growth from that without having to kind of go from scratch, improving these things. Right? So that's where I'm going with this. So that's why I showed this to you, a little bit tedious. Now let me show you what I think is a slightly better way. This is an alternative definition. In fact, it's going to be, I'm going to give you an alternative for each of those. So, what we're going to do is, no, we still want to compare f with g. You must first evaluate this number, if it's a number. Find the limit of f divided by g as n gets larger and larger. So what we're looking for is, how does this ratio look when you compare at a particular point the value of f divided by the value of g? And as n gets bigger and bigger, what does that ratio look like? So if g is growing much faster than f, then what you might expect is that that's going to go to 0, because you continue, you're ever dividing by a value that's larger than it was even before. And so what is it going to give us if you find this limit? If it comes out to a number, just from that number alone, we're going to be able to conclude, is it big O, is it omega, is it theta? Even is it little o or little omega? So here it is. So these are cases.
When you buffer from 120 to 7.
Don't make anybody queasy. Right, that mathematicians should get very annoyed with that. But right way to write that, because V is finite. All right, so as long as you don't get infinity, f is bigger of g. If v is strictly greater than 0, so it could be infinity for case 2, for the second case, then f of n is big omega of g of n. And the third one, if you remember, on Tuesday I was telling you that theta just means both big O and big omega. And you said, and I said to you, look, if something is both less or equal to two comparisons, both less or equal to and greater or equal to, then it must be equal. When you talk about real numbers, well, for functions, if two functions, and you compare them with both big O and omega of each other, then there must be theta of each other. Well, look at that. If in this context, with this new alternative definition, if the ratio of, the limit of the ratio, sorry, is finite and bigger than 0, then that means theta. So if now we can add, we didn't talk about, you may not have seen little o and little omega in discrete math, but I'll just add them here because it don't really take any more out of us to do that. So if you get that V is equal to 0, then F is little o of G of n. And the fifth one is if V is equal to infinity, then F is little omega of G of n. That thing that looks like a bent W is omega.
Zero or is it?
It's 0. I don't know that. Why is it little omega?
So, yeah, question.
Which one?
Don't 2 and 3 intersect. And 1. So that's, I kind of said it. Theta means both big O and big omega. So the intersection of 1 and 2 is what 3 is.
No, for the second one, if B is greater than 0. That can't be big.
I'm going to do an example so you can see.
That's little
When you say constant, it's going to come to a number, right? When you take this limit, now, there are some situations where a limit doesn't exist. In which case, we cannot conclude anything like that. But that's a different story. If the limit exists, it is a fixed number. The use of the word constant is a dangerous thing because clearly V depends on F and G, but not N. So I don't really think that V is a universal constant. It depends on what F and G are. All right, so let's do this example. Yes. What? So what? Yeah, for case 3. Wait, I'm not following. What is it? 1 is what? For case 1? You said 1 is greater than. So for case 1? Then 1, 2, and 3 hold. So what? So look, theta, when F is theta G, it means it is 2 things. F is theta G means F is big O G, and F is omega G. What do you mean by itself? You mean you want a case when F is big O G, but not big omega G? Then the ratio will be 0. All right, let's do an example. Let's do the example so you can see it. In a sense, one comment on the questions. Your questions reflect that your eyes are opening to just how wide those comparisons allow. Right, so maybe you didn't appreciate it before now. You might have thought theta is this narrow thing, like didn't really. It is relatively narrow because this ratio though is it's not gonna be arbitrary functions that will give you a non-zero or non-infinity answer. Okay, let's do a couple examples, and I'm hoping that you will see the simplicity with which you can apply this technique. So let's do the same question. So this is a proof that 3n squared plus 1 is big O of n squared. If you're trying to prove something is big O, of the other, according to this, we need to set the limit of the ratio and check which terms apply. Okay? So, just say,
I don't know. Because remember when you have this?
what does that limit look like? Well, that's 3n squared divided by n squared is 3, and that 1 divided by n squared looks like 1 over n squared. And as n approaches infinity, this approaches 0. So this limit is 3. And what that says is for it to be big O, it has to be less than infinity. Is 3 less than infinity? Yeah. So less than infinity, implying that 3n squared plus 1 is big O n squared. QED. Right? No searching, no guessing and spelling, wondering what C to use and what N not to cross that. Just set the ratio, find the limit, classify. Questions? Yes? It is not small o. Yeah, so this function is not little o of n squared. 3n squared plus 1 is not little o of n squared. And you can see how that's working out. Little o is supposed to mean much smaller than. 3n squared plus 1 and n squared are growing at roughly the same rate, up to constant. So that's what the theta is telling us. That they're, for all intents and purposes, if you're allowed to scale one by anything, the two of them don't have a huge difference in growth rate. But when you say small o, then that means that the one inside the brackets of the small o is growing much faster than the one being compared to it. Okay? And omega is just the sort of opposite side of it. All right. Any other questions? Correct. So you get immediately from this, we also know that 3n squared plus 1 is, okay, you could say omega n squared. And we also have we get all three conclusions from the same limit calculation. Somebody had a question? Yes. The limit, you understand what a limit is? That the question of the limit is, as n approaches infinity, what does this value look like? And as n approaches infinity, 1 over n squared disappears, becomes incredibly small, right? If n is 1,000, 1 over n squared is 1 over a million. That's a very tiny number. And as you increase n more and more, the 1 over n squared approaches 0 quite rapidly, actually, right? So what the idea of a limit is if you could get to infinity, what would that number be? Okay. I want to give you a couple of properties so you can appreciate how to combine these things. So now you have the kind of rudiments. If you have to prove something, how you do it, you can use that. Now here's handily, when we encounter these functions, we're going to want to be able to quickly tell what order of growth of something fairly complicated is. So I want to give you two general rules that you can then use for in almost every context, actually. If you know that f is big O G, which basically, remember in your mind, I want you to think, when you compare f and g, f is, in terms of the big picture, big N, f is not growing any much faster than the scale version of g. So besides g, f is kind of incomparable, or it's at the same scale, it's not changing, it's not bigger. Then what this means is that if I were to add the two together, the overall order of growth of the sum is not going to be any more than what I already had with G of n alone. Okay? And this comes down to because of those constants. Think of it like this. Since f is smaller than some scale version of g, f plus g must be smaller than some scale version of 2g, don't it? And 2g is clearly bigger than g because that's just a scale factor of 2. Okay? All right, another one. If f is bigger of g, then, and this one you can try and prove yourself, then it means that g is big omega of f. Does that make sense? Just stick with that less than or equal to analogy. If x less than or equal to y, then that means y greater than or equal to x. Yes? That's what this is conveying to you. All right. Now, let's see how you'd use this. All right, so here's one, 3n squared all right, that's one. Let's do another one. All right, we don't have more time to do anymore, so we'll stop there. Which of these? All right, so let's do the first one. When I ask you what's the order of growth of this, if you use these properties, you see that I'm asking to compare each of these with the separate terms, and whichever one would be the dominant term, that's the one that you're going to be left with. Because, so let me just illustrate that. I'll give you the answer to the first one, and then I'll illustrate why that's true, and you can understand what we're trying to do here. So, clearly 3n squared is bigger and theta n squared. That was what we proved over here already. Yeah? 3n squared is theta n squared. So I could have simplified this. There's no point me writing theta 3n squared. I could just write theta n squared. That's simpler. So this is already n squared. This one, 1000n, is theta n. Now if you're adding n and n squared, we know that n is bigger than n squared. n is not bigger than n squared, right? And therefore, if you add n and n squared according to this term, I could simplify that and just call it n squared. Big O. And if I add a constant to that, that doesn't change anything. So the whole thing could reduce to n squared. So all of this is delta n squared. Because the n squared term dominates the rest of it. That's another way to think of it. Now, of course, you could prove that for yourself. You could try and, take a comparison. Do this, divide by that, find the limit, and you'd find that, in fact, it's true. You get a ratio of 3 or something like that, and it's, oh, yeah, according to that. Yes? But when you're doing it, as in when you're mechanically, because these are kinds of expressions we're going to end up with. And what we want are these simplified versions of them without losing any information. So when you're doing this, you don't have to go going back to prove this. You kind of want to have an intuitive way of doing this. So when you're summing a finite number of terms, seek out the one that's dominant, the biggest one, and write it in its simplest form. That's how you do it. So exponentials compared to polynomials. Exponentials are always growing faster. You can say it to 2 to n. N plus log of n squared. N dominates. Log of n squared is actually just 2 log n. And log n is much, much smaller than n. So scaling it by 2 doesn't change it. 1/1000 n cubed plus 100,000 n squared. Yeah, the n cubed. Don't be fooled by the constants. You get a lot more practice in the tutorials, but that's it for today. If you have any, unless you have questions.
Excuse me, sir.
Okay.
Hello.
So I'll see you on Monday.
Oh my
God. Keep an eye out for that POTW0.
Sir. Hello, sir. Wait, no, the mic's here, right? Hello, sir. Messages, that's why I sent it.
Professor Core, I believe Kirill has a question.
Yeah.
Hello.